Hi, in this example, we're going to do sketching the curve following the process of calculus, right? So again, we're going to do the algebra first, then first derivative stuff, and then second derivative. Now, as we can see with this function, that this function is rational. So we're going to not only have to talk about domain, but we definitely have to talk about asymptotes. And I can see already because the degree in the denominator is larger than of the numerator, I know that we're going to have some some asymptotes here, especially vertical ones. So for the domain for rational functions, we recall that the domain for rational functions is everywhere else but excluded values. The only time we exclude values is if there are certain restrictions on functions, like this a radical denominators like here. So denominators can't be zero. We learned that all the way from arithmetic. So now that we have variables in our denominator, we definitely have to worry about this. Is there a number that we can plug in for x such that we would have zero in the denominator when I evaluate? And I can easily see that this is so. Right, I easily see I can put in a 3 there, and a 3 squared is a 9 minus 9 is 0, or a -3. So I do know that the domain will be all real numbers except for -3 and +3. So we can rewrite this several ways. Let's see, negative infinity to -3, union, -3 to 3, union, right? We had to skip over 3 to infinity. We had to skip over all those intervals, right? All those threes. Okay, for intercepts, we know that for intercepts, so now let me put one and I'll put algebra. That's always the first part, right? So for the y-intercept, we just go ahead and plug in x equals 0. If I put in 0 in for x, I can easily see that I'm going to get 0 over -9. So that y-intercept will be 0. And I can go ahead and put that right there. The x-intercepts are a little tougher, right? They are when y is equal to 0. However, with rational functions, I'm going to write this down. So with rational functions, okay, the function is 0 where the numerator is 0, okay? The rational function's undefined when the denominator is 0, right? We recall this from our algebra. So this would mean if I just scoot up a little, and rewrite the function y equal x over x squared minus 9, where it would be 0 is was 0 equal to x over x squared minus 9. And I would only look at the numerator, right, where the numerator is 0. And I can see once again, x is equal to 0, and that's the only x-intercept. The x-intercept and the y-intercept are the same point. Okay, the next part is we have to talk about these asymptotes. I do see that there's a vertical asymptote, right, where the denominator is 0, and that's, where the excluded values lie. So we do have a couple of vertical asymptotes at x equal 3 and x equal -3. The horizontal asymptote this is a proper fraction. That's what I call it. When the degree in the numerator is smaller than the denominator, that is a proper fraction. And we do have a horizontal asymptote. It's just that x-axis, that y equals 0. And we have more resources in the chapter 1 folder. I have a couple of pages that I wrote up about asymptotes with rational functions. So we just have to be careful here. And then I know it didn't ask for the asymptotes, but it's very important that we note this. So I'm just going to do this so we realize that. Okay, so that's it for the algebra part. That's the shortest part, right, for rational functions. Now let's go ahead and move on to the first derivative stuff. Recall the first derivative stuff will give us local extrema and increasing, decreasing intervals. So here, I'm going to put first derivative, Okay, and let me write the function x over x squared minus 9. Okay, so the first derivative here, I agree it's not going to be easy, but it's not hard. We just have to apply the quotient rule. I encourage the quotient rule. You don't have to. You can use that product rule by putting that denominator to a power of -1, or product rule. But I'm easy peasy, and I just like rather use a quotient rule. So I'm going to go ahead and draw a bar here. And I'm going to put the denominator on the bottom, x squared minus 9, and square it, bring it up, don't touch it, times the derivative of the numerator. So I'm going to put that in red so we know we took the derivative, minus the derivative of the denominator, which is 2x, and then times, leave the numerator alone. So here we have x squared minus 9 minus 2x squared all over and x squared minus 9 squared. So you could see that wasn't too bad. And if I simplify that, I'm going to have x squared minus 2x squared. So I'll have a negative x squared minus 9 all over x squared minus 9 squared. I wouldn't reduce out a factor because of this negative x squared lingering. It's not identical to the denominator. The denominator has a leading term that's positive. So we just have to be pretty careful with that. Okay, so this is the first derivative. We would now want to find critical numbers of y, which is where y prime, sorry about that, is equal to 0 or undefined. Okay, so let's go ahead and set that first derivative equal to 0, and that's equal to negative. And again, I like personally changing those x's to c's because c is for critical number, and it keeps me straight. I'm not confusing my domain values with my critical numbers. There we go. Okay, once again, where a rational function is 0, I wrote it up here, is where the numerator is 0. So all we're going to do is set this equal to 0. So now we have 0 equals negative c squared minus 9. And I'll just move the c squared over like that. And we see that c squared cannot be equal to negative 9 because that would make it imaginary, complex, and so therefore we do not have any critical numbers, no critical numbers where the first derivative is equal to 0. However, we do have some critical numbers in the denominator where it can be undefined. So here, where it's undefined is still at that positive and -3. Right? If I put -3 in there, it would be 9 minus 9 is 0, and 0 squared is 0. So once again, we still have critical numbers of plus and minus 3, and this is where y prime is undefined. So we still have something to work with. However, these are undefined, right? These are vertical asymptotes, but there's behavior happening around them. Right? We don't care what's happening there. We just care what's happening around them. So I'm going to try to fit this here. So here's -3, here's 3, and there's my little thing. I'm going to circle my critical numbers. And then I'm going to have y prime up there and the behavior of y down here. And of course, I'm going to pick 0, and then I'll just pick -4 and then 4. That's easy. So if I put in -4 into my first derivative right here, I get negative on top and positive on the bottom. So that would mean that would be negative. If I put in 0 in my derivative here, I get a negative on top, 0 here, and negative on the bottom, right? Positive here, negative here, which gives me another negative number. And if I put in 4, I get 4 here, which is a negative number. And then over here, over a positive number, it's that square that always is going to make that denominator positive. And therefore, we get another negative. So what does this mean to our original function? Well, that it's always decreasing. And if it's always decreasing, we have no relative extrema. So this would mean that we have no extrema, right? No local max, no local min, but we do have an interval of decreasing. We don't have anything increasing, it's in decreasing forever, right? So let's go up there and fill that in. So we have no local extrema, so we are going to have none here. And then on increasing, we're going to have no intervals of increasing, but decreasing forever. But again, we do have these jumpers, right? So we're going to have to do negative infinity to -3 union, -3 to 3 union, 3 to infinity. Right, I call them jumpers because you got to jump. All right, and now we can see the last piece are the second derivative category, right? So now we can do the second derivative. Again, methods never change, only problems do. Algebra first, whatever that entails, first derivative, and now we can do the second derivative. So let's go ahead and do that. We know that the first derivative is -x² minus 9 all over x² minus 9 squared. Now, it depends how you want to do this. This is the part actually it will take the longest. Other than that, testing and stuff is always quick. So let's go ahead and try that. So the second derivative, I'm going to do quotient rule here. So I'm going to have x² minus 9 squared and then square it again, right? It's the denominator squared. Bring it up, don't touch it. So x² minus 9 squared times, and then take derivative of your numerator, which is -2x. Okay, minus, now we're going to have a little work here. Let me draw this line even longer. Now, again, I took the denominator here and squared it, brought it up, took derivative of the numerator, minus, now I have to take the derivative of the denominator. This is going to take some chain rule here, right? I have to bring down that power of 2, multiply by the inner, and that becomes just one factor, times the derivative of the inner, which is 2x, because that was the derivative color, and then times, leave the numerator alone, -x² minus 9. So what I'm going to do here is a little algebra trick I love oh so much, right? Here, I see a common factor here. This is all product, nothing subtracting. I can take out one factor of x² minus 9. So I'm going to take out x² minus 9 and leave in big parentheses everything else. I have, if I take out one factor of this, I have one factor of it times -2x. So I'm going to have -2x times x² minus 9. Minus, and if I take out this completely, I'm only left with the 2 times 2x, so 4x, times the numerator, which is -x² minus 9. All over, which, there we go, x² minus 9 to the 4th power. Great, and now let's reduce it out. So I'm going to reduce out one factor of x² minus 9. I'm going to go ahead and simplify what's inside here. So I'm going to have now on the top, let's do it up here. Maybe we can see it better. We're going to have -2x cubed plus 18x, right? That's what happens when I put it in there, right? Next, I'm going to have -4x times -x², which will give me a plus 4x cubed and a plus 36x. So what does that look like? So on the numerator now, we're going to have 2x cubed, okay, plus 54x all over the x squared minus 9 cubed. Now we can do a little more here, but I think this is good enough because all we really do need is the critical numbers, right? So now what we're going to do, because we're looking for points of inflection and concavity intervals. So now we need to do is find critical numbers of the first derivative, which is where the second derivative is 0 or undefined. Okay, so here, I would set it equal to 0, equal to 2, and then again, it's a rational function. And the only time that the rational function is 0 is where the numerator is 0. So we're going to go ahead and put 2c cubed plus 54c. Okay, and I'm just going to factor out the GCF of 2c and get c squared plus 27. And therefore we get c is equal to 0. I'll put it here. And then c squared plus 27 equal to 0. Now, right away, I can see that c equals 0 is going to be a point of inflection. But over here, again, if I move that 27 over, this is a complex number. And so we have to omit it, right? So here, notice that not only is 0, 0, this is the ordered pair 0, 0, right? It's not only a point of inflection now, it's now an intercept too. It's X and Y intercept and a point of inflection. So let me put that there. Right. Now, all we need to do is test for concavity around this point of inflection. So here I can just put 0 here and then circle it. We still have those undefined values no matter what. Maybe there has to be behavior still at the critical number plus and minus 3. I just see this here and I still get worried. So let me put that here, -3, like that. Okay, and maybe try the -1 part, 1, and then a 4 and a -4. Just feel like things are happening. So if I put in a -4 there, I'm going to get a negative number there. If I put in a -1 in there, it's going to be positive. It's going to be concave up in between -3 and 0. And if I put in a 1, and you can do this yourself, right? Put in a 1 there and see if you get positive or negative in that second derivative. And you would get, and you can know the pattern here. It's going to go minus and then plus. Right. So here, what is the original function doing? Well, it's going to be concave down over here, concave up, concave down, and concave up. So we can see that the 3's are not points of inflection, they're asymptotes, right? But that point of inflection is going to be at 0, 0. And then the concavity intervals is where these 3's are going to be our barrier. So here, let's go ahead and do that. So concavity would be down from -infinity to -3 and in between 0 and 3. So down from -infinity to -3 and then union back over from 0 to 3. Concave up, we see that it's going to be from -3 to 0 and then 3 to infinity. -3 to 0, concave up, union, and then from 3 to infinity. Okay, and then from here, I'll go ahead and leave graphing to you with the ordered pairs as you saw in the previous practice problems. But I do hope this helps. And it does look something like if I kind of showed it here, maybe I could do it like, there we go. So it looks something like that. That's how I did it on my paper. So you can go ahead and graph and make sure, but again, I feel like the graph is always something that you could verify technologically, but like the process, right? The algebra part, first derivative, second derivative, and I used everything I possibly could. I used chain rule, I used quotient rule, I used undefined, right? So again, just the methods never changed, just the problems do. And so make sure if you can get this method down, you pretty much have everything in your life in math up into this moment. So, okay.